all the people who have joined today. So today on the Control Conclave, we have with us Mr. Michael West. Uh, Michael West is a PhD candidate in mechanical engineering at the Department of in the Department of Mechanical Engineering at MIT, USA. In 2018, he graduated from Yale University with a bachelor in mechanical engineering, and then he received a Master of Science in mechanical engineering from MIT. Currently, his research focuses on investigating how humans are able to manipulate and physically interact with complex objects. Additionally, he has explored how humans perceive underlying dynamics purely based on visual observation of motion. His work aims to provide a greater understanding of human motor control in an effort to design better control algorithms for robots involved in physical interaction, human robot collaboration, and robotic rehabilitation. So Michael has received various prestigious fellowships because of his work, like the Ben Gold Fellowship, the Takeda Fellowship, and the GM University Associate Fellowship. So this was a brief intro about our speaker, and he will be speaking today on the topic mechanical impedance, a necessity in both human motor action and human motor perception. So with this, I will hand it over to Aaron. Over to you.
So, see if I can share my screen. You guys seeing the correct screen?
Yep, we can see it. Please.
Okay. Thank you for the wonderful introduction. I appreciate those kind words. So, as Udan mentioned, um, my talk today will be on mechanical impedance and why it is a key component in both human motor action and motor perception. Uh, So getting right into it, in our lab, we study how humans manage physical interaction. Specifically, we want to understand from a control standpoint, how do humans control movement so that we can implement this on robots. In the video shown on the left, you can see some humans successfully managing their everyday complex physical interaction tasks. On the right, you see some of the most advanced humanoid robots at the DARPA Robotics Challenge failing to do tasks that we humans find trivial, such as getting out of a car, walking in sand, or opening and walking through a door. What makes this most interesting is when you look at humans' wetware and hardware. For example, human actuators, the muscle, is about an order of magnitude slower than the actuators of robots. And additionally, we have communications that are 6 orders of magnitude slower than those of robots. And then we have feedback delays, which are about 2 orders of magnitude greater than that of some of the most advanced robots. So with that understanding, it appears that humans are doing more with a lot less. So we ask the question, what enables this paradox of human performance? One proposed solution is this idea of dynamic primitives, which are a set of innate actions that simplify the control of the otherwise complex neuromuscular system. Professor Hogan and Professor Sternad have identified 3. However, today I would like to focus in on mechanical impedance as it has been proposed specifically for managing physical interaction. Mechanical impedance is the dynamic relation between motion and a resultant force, and oftentimes it can be modeled as a spring mass damper system as shown in the figure here. And lastly, I previously presented mechanical impedance as a feature. However, I do want to talk about whether it can be a bug and if it has some limitations as well. So in human neuromotor science, this idea that human motor action and motor perception is coupled is very widely accepted. And what that necessarily means is that when you interact with an object, it can change the way you perceive it. And similarly, when you perceive an object, it may change the way you control your own actions. I think the best way to internalize this is thinking about how babies may learn. So in fact, babies come out the womb not necessarily knowing how to walk or not knowing how to walk or talk. However, from observing the peers in their life and adults in their life, they're able to now learn something about how adults walk, and then they can change their own controllers and learn to walk themselves. And today I want to talk about how mechanical impedance is a part of this human motor action, motor perception relationship. And I'm going to do that by presenting 2 works of mine that have been recently published, one in the motor action domain called Human Force Regulation During Motion, and one in the motor perception domain titled The Visual Perception of Stiffness. So starting in the motor action domain, uh, oftentimes in robotics, when you have to interact with an object, in addition to controlling position and some space, you also have to control the force, the interaction force. And in robotics, this is done in often in two ways. You can have a compliant controller, or you have a hybrid controller. In hybrid control, it assumes you can control both position and force simultaneously, so long as they act in orthogonal positions or orthogonal directions. And oftentimes, this has led to people in human controls to assume that humans can do this as well. And in fact, oftentimes roboticists will use this idea of trying to measure directly force during motion to measure human intent. And some examples are listed. However, I want to probe into this question and ask specifically, can humans actually manage direct force control during motion? Rather, can humans directly control their force independent of motion? And upon asking that question, which I'm going to convince you of today, or aim to convince you of today, is that humans actually cannot manage direct force control. They cannot control their force independent of motion. And the reason they cannot do this is because motion is coupled to force inherently when humans do physical interaction tasks. And we've coined this term, or we've in our paper we've coined this type of controller an indirect force controller. Then, with an understanding of the fact that mechanical impedance is important in the motor action domain, moving into the motor perception domain, we were curious to ask the question, okay, well, if mechanical impedance is a part of our motor controller, our action controller, is it something that can be perceived as well? And specifically, a colleague of ours, Professor Huber at UMass Amherst, previously asked, can humans perceive limb stiffness from visual observation of motion? And what she did was have subjects look at this two-link manipulator, this video that you see playing here, and then just simply rate its stiffness. And in fact, she found that people were able to, estimate changes in stiffness from this visual observation of motion. However, the question remained how? That's the question that I aim to answer. And in aiming to answer that, I drew upon, again, this motor action, motor perception relationship and hypothesized that, okay, well, the simulated motion that produces this two-link manipulator, the controller used to produce that simulation has to be somewhat congruent with humans' own internal model of motion. And specifically, from that hypothesis, I was curious, okay, well, what motion cues are humans using to estimate stiffness specifically? I think one thing that's important to highlight here is that people are estimating stiffness purely from visual observation of motion. And inherently, stiffness is a relationship between motion and force. So if we think about that in its simplest terms, we can think about Hooke's law, which F equals kx. People are inherently solving for k without any F, without any force information, just solely x, just displacement or motion information. So the question becomes, okay, well, how are they doing this? What specific motion cues are they looking at? So to give a high-level overview of my presentation, more bluntly, I specifically asked and answered three questions. First, in the motor action domain, I asked, can humans manage direct force control during motion? Secondly, in the motor perception domain, I asked, what motion cues are humans using to estimate stiffness? And then finally, I want to briefly touch on whether mechanical impedance is a bug or a feature. So first, starting with our experiment in the motor action domain, I wanted to experimentally test the hypothesis that humans can regulate force independent of motion. And what do I mean by that? Well, I refer to independent control of force and motion up here as direct force control, in which you have a planned force, and there may be some forward path dynamics that affect your planned force, but theoretic or solely your applied force is solely a function of distance. Now, if this formulation turns out to be true, when you ask subjects to do a force control task or apply a force during motion, errors in their contact force should be independent of motion. However, if this hypothesis turns out to be false, I propose this indirect force control method where we may still have some sort of planned force that leads directly to our output for our applied output force through some sort of forward path dynamics. However, more importantly, we now have this highlighted impedance term, where again, our planned motion directly affects our applied force. There are two important considerations for the indirect force control is that indirect force control leads to direct force control under two conditions. One, if this impedance term is, or this impedance mapping is 0, which in humans we found not to be the case, as muscle dynamics, muscle impedance is rarely ever able to be eliminated or go to 0. And then secondly, if the input motion, the output of your forward path dynamics from your planned motion is equal to your actual motion, then again, this term here becomes 0 and your indirect force controller looks exactly like your direct force controller. However, the key takeaway from here is that if humans are doing direct force control, meaning they can manage force independent of motion, then when we do have them do a force control task, then errors in contact force will be independent of motion. So how do we experimentally test these two opposing controllers? Well, what we did was we had subjects sit in front of a robotic manipulandum, as shown here, and the manipulandum moved in the transverse plane about an elliptical trajectory. They're specifically asked to apply a 5 Newton force in the tangential direction of motion on the robot's handle. Important to emphasize here is that subject sat in front of this robot manipulandum, and the robot provided the motion all on its own. If the subject didn't touch the robot, it was going to move along this elliptical trajectory with very high stiffness gain. All subjects could do was apply a force to it, so they couldn't provide motion to the robot. So after being instructed to apply 5 newtons of force in tangential direction, the experiment was furthermore split into 5 blocks consisting of 15 trials each, where each trial consisted of 4 cycles around the ellipse. So meaning in total, subjects traversed this exact same ellipse 300 times. Moreover, each block oscillated between not giving visual feedback, giving visual feedback, not giving visual feedback, and so forth. And the visual feedback looked like so, where they saw this projection screen in front of them, this black projection screen in front of them that had a static white bar, which was the target force, the representative of the target force, and there was this moving red bar that moved vertically in plane, which represented their actual force. So essentially the name of the game was to get the red bar on top of the white bar. Additionally, we were able to obtain data from a colleague, Pauline Maurice, who conducted a 2017 study, who had the exact same conditions as a similar part of her study. However, the only difference was that she asked subjects to apply a 0 Newton force on the robot manipulandum, and only in one block that consisted of 10 trials with no visual feedback. Specifically in her experiment, she focused on asking the question, which velocity profile should the robot manipulandum follow to best enable human interaction, which she quantified with this 0 Newton total force. Her study concluded that the velocity profile should follow the 1/3 power law, which is a velocity profile found to be congruent with upper limb region. This mathematical relationship shown here states that the tangential velocity is proportional to some gain k times the radius of curvature to the 1/3 power. However, rather than think about this mathematically, the best way to internalize this formula is that when you're going around this ellipse, you move faster along the straightaways, which is shown by the yellow tangential velocity here, and you move slower around the curves, around the more curves area. And this formula directly quantifies that speed based on this radius of curvature. And as Marie said, all found that this velocity profile, this 1/3 power law, enabled the best interaction for humans during this task. We incorporated it into our study as well. So in our study, when subjects were going about this ellipse, it followed the 1/3 power law. So what were the results? So the first result is when we look at the experimental blocks, here we see the root mean square force error as a function of trial numbers separated by the 4 experimental blocks. And then for the 5 Newton experiment and the 0 Newton experiment, the first thing we see is that there's limited improvement in force error over practice. What we did to quantify this is for all the subjects, we took their force error in a given trial, the root mean square force error, and this is plotted here in the shaded regions. And we fit a linear model to that data. And from that linear model, we were able to obtain a correlation coefficient, and we statistically determined if that correlation coefficient was significant. And if it was significant, we said subjects learned in that trial. And interestingly enough, subjects only learned in this first block. which makes sense. In the familiarization block, people they're given a familiarization block to get used to the task. They weren't given any idea what 5 newtons of force is. If I tell you right now to apply 5 newtons of force in your computer, you probably wouldn't necessarily know what that information is. But once we give you visual feedback, as we did right here, then you start to be able to reduce that error. However, one key takeaway is that despite extensive practice, subjects could not further reduce their error. So once we get to this point, recall that subjects had gone around this ellipse 300 total times. And we can see that their root mean square force error on average is still about 4 newtons. So the question becomes, okay, well, why can't subjects further reduce their force error? And the answer to that question is periodicity. Recall the hypothesis of direct force control. So if humans can manage force independent of motion, errors in contact force will be independent of motion. So what that means is if we were to take the force signal and plot it as a function of position, and we took its autocorrelation, if the force was independent of position, then we should see an autocorrelation function that looks something somewhat like this Gaussian noise. However, if it is periodic, meaning that the force is a function of position, then we'd see an autocorrelation signal that looks somewhat periodic, like so, shown on the right. So, in fact, looking at this representative subject in the 5 Newton experiment in both the familiarization block and the last block, what's plotted here on the left is we have subject's force plotted as a function about the ellipse, where the colored lines are just different trials, and the darker line is the average across all those 15 trials in this given block. And what we see is this function is clearly very periodic. And when we take the autocorrelation of these functions, we see that there's these peaks at about 180 and 360 degrees. So the key result here is that the applied force is not independent of motion. In fact, when we look at this force, it is clearly a function of motion. So as seen previously on the representative subject graph in the previous slide, the force error is periodic and motion dependent. And what we did to quantify this periodicity, as alluded to before, is we computed the autocorrelation function of each subject's force signal and found where the lag of maximum autocorrelation occurred. And as seen in this graph here, essentially there's peaks at 180 and 360 degrees. So these graphs show the peak or the maximum lag of the autocorrelation function of all the subjects. This is in the 4 experimental blocks and the 5 Newton experiment. And this is in the familiarization block in the 5 Newton experiment. So this is the first block when a subject just got in front of the robot and started to interact with it for the very first time. And then again, we see that in the experiment or in the 0 Newton experiment block which is the data we obtained from the Pauline Marie's 2017 study. So what this says is that this observation is robust across all subjects in both experiments, independent of feedback condition and independent of practice. Recall the familiarization block is right when they get in front of the robot. We see these peaks at 180 and 360 degrees in their force error, or in the periodicity of their force error. And then we also see it across just multiple different levels of applied force, and also different levels of whether there's feedback or not. So what this suggests is that the periodic force error seen here suggests that a controller appears to be content with good enough performance, which can be obtained using a limited set of primitive oscillations with a sufficiently low mechanical impedance. So to conclude, despite extensive practice with this robot manipulandum, the subjects were unable to further reduce their force error in this simple force control task, where they were just tasked with applying constant force on a moving object. And in fact, the errors in the force were motion dependent, suggesting a coupling between motion and force. And this can be described by mechanical impedance, as in the indirect force control method that we talked about earlier. And this periodic motion is consistent with the theory of dynamic primitives, of oscillatory primitives, where you may have an oscillatory input into your motion planning controller and both your indirect and your indirect force controller, which can lead to sinusoidal outputs in your applied force. And in fact, the key result is that we have a mathematical model which combines these oscillatory primitives with mechanical impedance, which is somewhat competently enough able to describe the results that we saw in this physical interaction study. So this work, I would argue, is of particular concern in one, human quantification of performance, and two, estimation of human intent. So taking a step back and thinking about, okay, in this task, we asked someone to apply a constant force. What we found was that, sorry, what we found was that people were unable to apply a constant force. So if we were to go ahead and create a measure of trying to understand, okay, someone's trying to apply a force, and we use this output of if we use the output of the force that we measured here and it was sinusoidal, we'd assume, okay, they want to apply a sinusoidal task. However, that's incorrect because the subjects in this task were trying to apply a constant force. So now that we have an understanding of mechanical impedance in the motor action domain, let's take a look at its role in the motor perception domain. So as we know, and because as we know, humans in humans, motor action and motor perception are coupled. So there's this interesting phenomenon that shows that humans can extract latent information from visual observation of motion. This is best shown in point light animation. So in the video shown here, you can see just from recorded dots on people doing a task, you can very easily tell that the person was walking, jumping, or climbing stairs, and even here sitting. And in fact, these studies have been shown to show that people can tell different gender, different age, different moods, just from these point light animation studies. So humans are able to really achieve just a lot of latent information from just visual observation of motion. And this phenomenon led Professor Huber at UMass Amherst to ask the question, okay, can humans perceive limb stiffness from visual observation of motion? What they did was have subjects sit in front of a computer screen, observe a two-link manipulator move, and then tell them estimated stiffness on a Likert scale from 1 to 7. And they found that, yes, subjects were able to do this. However, the question still remained how. And as I said previously, the hypothesis based on this motor action, motor perception relationship is, okay, well, clearly mechanical impedance is a part of the motor action relationship. If we create this simulation that has mechanical impedance in it, then people should theoretically be able to perceive it as well. However, that doesn't necessarily give direct information onto what specific motion cues humans are able to use when estimating stiffness. So I hypothesized that subjects were able to do, I hypothesized that subjects were able to do this task because there was a consistency between how humans did the consistency between the simulation that was used and how humans control their own method. And recall in the previous study by Marie et al., where they had subjects interacting with the robot manipulandum at different velocity profiles, they found that the velocity profile that followed the 1/3 power law gave the subjects the best ability to interact with the moving robot. Furthermore, in the literature, this 1/3 power law phenomenon is widely reported to negatively affect aspects of humans' motor perception as well. And this 1/3 power law has also been found to be consistent with how humans move in free space in the upper limb region. So all that's to say, in the original experiment that Professor Huber ran, their simulations generally followed this 1/3 power law. Thus, I hypothesized that manipulations to this velocity profile that violate this 1/3 power law should inhibit subjects' abilities to estimate stiffness. So, as I said, what Professor Huber previously did was she had subjects sit in front of a computer screen, observe this two-link manipulator move, and then ask them to rate its arm stiffness on a scale from 1 to 7. These subjects watched 30 simulations, which consisted of 6 different values of joint stiffness, which I'll go into later. And they were shown these values in a block randomized order 5 times. And they were able to, correlate the simulated stiffness, these 6 conditions, somewhat to their arm stiffness ratings on a scale from 1 to 7. And the question was how? Okay. And I said the reason that people were able to do this task is because there's a congruency between their controller and the simulated controller. So now it's important that we take a look at the simulated controller in this task. So the simulated controller looked like so. where the output torque is described by this equation that may look somewhat complex, but it's really simple. And the fact that there are two attractors. There's this endpoint attractor, which attracts the endpoint about elliptical or a circular trajectory, and has a damping to ground. And then there's secondly a joint space attractor shown here by these springs, which pulls the joints to a nominal configuration. And I guess it's important to highlight the arm was moving in the vertical plane, subject to gravity, and it was given typical arm dynamics consistent with that of an adult male. So I guess importantly, in this joint space attractor is in Professor Huber's simulations and simulations I'm going to present, these values, this KQ term, the shoulder stiffness and elbow stiffness of these two joints are what were modulated. So inherently, that's what we are asking subjects, or that's what we were trying to see if subjects can tease out the difference in these values, and in fact they could. So from Professor Huber's studies, two open questions are made. What motion cues are humans using to estimate stiffness? And are they looking at path information, or is temporal information important as well? And by path information, I mean specifically displacement, and by temporal information, I mean velocity and its derivatives. So to answer this question, I conducted 3 new conditions where I kept the path information the same, but I manipulated the temporal information, or specifically the velocity profile. And I manipulated the velocity profile in ways that violated this critical 1/3 power law. So given the power law, where we have this beta term here, which is originally 1/3, which is vertical, what I did was I presented 3 new conditions where I have the this beta term, or the power, set to 0, which leads to a constant velocity. So shown here is a 2-link manipulator, and these are the paths that the manipulator followed based on the simulated joint stiffness. And this was consistent across all 4 conditions, the original experiment that Huber ran, and then 3 new experiments I ran. However, what's changing here is you see, based on this constant condition, constant velocity, when we look at this velocity profile, we look at the velocity based on the color scheme shown here, we see that this is all the same. We have a constant velocity. In the second condition, we set beta to the -1/3, which is a reverse velocity radius of curvature relationship. So in the original condition, recall that we said along the straightaways, we went faster, which is shown by the blue colors here, and around the curved edges, we went slower, which is shown by the red colors here. So the reverse condition is the opposite of that. Along the straightaways, we go slow, which is shown by the red color here, and then on curves, we go fast. And the third condition did not follow consistent velocity radius to curvature power law relationship. It was variable. So these are the 3 new conditions. And again, we hypothesized that these manipulations to these velocity profiles should inhibit subjects' ability to estimate stiffness. So what we found was pretty remarkable. Despite manipulations to the velocity profile, subjects could positively correlate their stiffness ratings with the simulated joint stiffness. Shown here, we see subjects' simulated joint stiffnesses plotted as subject stiffness ratings, which they rated on a Likert scale from 1 to 7. And we see in the original condition and all 3 of the new conditions, we see a positive linear effect of simulated joint stiffness on stiffness rating. And shown over here, we see each subject's individual stiffness ratings, where the dots show the stiffness rating, and larger dots show greater significance of the stiffness rating. But what's important is that we fit a linear model to subjects' data. And from that linear model, we were able to attain a coefficient of determination, which was used to measure the subject's ability to estimate stiffness. So shown here is the average coefficient of determination for each of the experimental conditions, the original, constant, inverse, and variable conditions, variable power law conditions. And what's shown here is that the condition had no effect on subjects' ability to estimate stiffness. Again, one thing that we did to again probe at what aspects of motion subjects were using to estimate stiffness was we simply asked them. So after subjects completed the experiment and observed all 30 simulations, we asked them to open-endedly write down how they estimated their stiffness. And what we were specifically looking for were 4 categories of information. We were trying to see if they looked at path information, temporal information, joint motion, or endpoint motion. And as I said before, we had subjects open-endedly write down what they use. So to try and codify this into a way of teasing out these specific aspects of motion. Sorry about that. Teasing out these specific aspects of motion was we codified the response by looking for keywords or phrases. So for path information, if subjects use the word distance, displacement, range of motion, or angle, we said they looked at path information. And if these words did not exist, we said they did not look at path information. If subjects use the words speed, rate, acceleration, jerk, or smooth, we said they looked at the word, they used temporal information. And if they didn't use those words, they did not. Similar, and then for joint motion, we looked for the words joint, shoulder, elbow, and angle. And then sometimes subjects drew a picture of the arm and pointed at, or of the manipulator and pointed at what areas they were looking. So if they pointed at, the joints, we said they were looking at joint motion. And then similarly for the endpoint motion, if subjects use the words endpoint or had a hand-drawn picture to the endpoint of the manipulator, we said they looked at endpoint motion. And what's important here is that most subjects reported using path information and joint information. Moreover, binomial regression was conducted to assess the effect of condition on the likelihood that subjects reported using path information, temporal information, joint motion, endpoint motion to rate stiffness. And results of the binomial regression showed that the condition did not significantly affect the subject's likelihood to report using any of the 4 motion features. Moreover, when we look at the subject's ability to do ability to estimate stiffness based on the coefficient of determination, we use linear regression to determine if there was an effect on subject's ability to estimate stiffness based on this coefficient of determination, and we use linear regression to further investigate the reported use of certain motion features coded down here on subject's ability to estimate estimate stiffness as quantified by this R-squared value. And what we found was that none of the 4 motion features were significant predictors of subjects' ability to estimate stiffness. So whether subjects said they estimated stiffness with path or temporal or joint information or endpoint information or any combination of the 2 or any combination of the 4 did not affect subjects' abilities to estimate stiffness as defined by this coefficient determination. However, another important thing to highlight is that shown here, many subjects could not actually articulate which strategy they used to estimate stiffness. I think this kind of alludes to the point that this action of estimating stiffness is somewhat innate to us and done subconsciously, which is why subjects may not necessarily be able to articulate what they are doing when they're doing this task. They're clearly able to do it, but they're not able to articulate how. So in the previous set of experiments in this motor perception domain that I talked about, we found that manipulation of temporal patterns did not preclude subjects' ability to identify changes in simulated joint stiffness. However, it is still possible that temporal patterns influence human stiffness estimates. And we were not able to eliminate that with that set of studies, eliminate that hypothesis that temporal patterns did have an effect. So what we did to determine if temporal information does influence humans' estimates of stiffness was we showed subjects the same path information. However, we manipulated the temporal information now. And then again, we asked subjects to write down the strategies they used to estimate stiffness after the set experiment. So I guess to state this more clearly, we had subjects again sit in front of a computer, observe this 2-link manipulator move, rate its arm stiffness from 1 to 7. However, this time they watched 20 simulations, which consisted of 4 temporal conditions with 1 value of simulated joint stiffness. So the simulated joint stiffness and the path information they saw was exactly the same 20 times in a row. However, what changed was the velocity profile. And they saw these 4 different velocity profiles, 5 times each in a block randomized order. So, and what we found was subjects rated the vertical velocity profile significantly lower than the manipulated velocity profiles. However, there was no difference between the manipulated velocity profiles. And then when we look at what subjects reported using, one thing that we see here is that more subjects reported using temporal information. More subjects reported using temporal information in this study, which makes sense. The difference in path information was indistinguishable. It was exactly the same every time in a row, which kind of leads us to believe that, okay, that temporal information does have an effect. Specifically, people perceive manipulated velocity profiles to have higher stiffnesses than vertical velocity profiles. And I think one interesting thing to highlight is that in the previous set of experiments where there were differences in path information, only 23% of people reported using temporal information. However, here, 80% of people reported using temporal information. So to conclude, humans can correctly infer changes in limb stiffness from non-trivial changes in multi-joint limb motion. And this suggests that stiffness, or more generally an aspect of mechanical impedance, is encoded in subject's internal model to do this task. And again, to do this task, I am referring to the motor action, motor perception relationship. People are able to perceive this task because it is part of their motor action controller. And then one thing the new finding of this study was that people can do this despite manipulations to the velocity profile. And the reason people are able to do this is from the fact that path information predominates temporal information in the ability to do this task and the visual perception of stiffness. However, simulations with a vertical velocity profile were perceived as less stiff than simulations with a manipulated velocity profile. I think this is a subtlety that's important to highlight, and the fact that what we are claiming is that temporal information is not important. However, path information is more important in people's ability to estimate stiffness just from visual observation. And as an impact, what we've learned from this is that we've used this motor action, motor perception relationship to learn, or to use a perception task to learn more about humans' motor actions. And then secondly, I think this method suggests a new minimally invasive way to measure stiffness. I personally think this could be an interesting future line of work, because currently to measure impedance, one must apply a force and measure resultant displacement. However, that is often encumbering and can inhibit someone from doing the task they set out to do. However, today I've shown that humans can estimate force just by measuring displacement. Presently, there exist many methods of obtaining this kinematic data non-invasively using video information, such as software packages known as OpenPose or Deep Lab Cut. So if humans can estimate this latent information or stiffness from only kinematic data, and I can figure out how, then we can possibly use these new softwares to build a system that can also extract mechanical impedance from kinematic data collected via video. And this would lead to a new minimally invasive technique to measure stiffness. So lastly, I want us to talk about whether impedance is a bug or a feature. Well, my answer to that question is both. And when we look at our human force regulation during motion study and the human motor action domain, we saw that we asked people to apply a constant force during motion. And the fact that subjects were unable to do this because force was motion dependent led to subjects being unable to apply this constant force. So in this case, this served as a bug, a limitation. However, in the visual perception of stiffness task, we can argue that this is a feature, right? And I think the best way to sort of internalize this is in human collaboration. I think oftentimes when you go and shake someone's hand, you may want to try and decide how firm your grip wants to be before you touch that person's hand. You can go ahead and you can sort of look at their hand and see, okay, this is how stiff their hand is. Similarly, for other interaction tasks, you can sort of perceive someone else's motion and their intended motion because you have some sort of understanding of their underlying controller. I think this can also be extended to human robot collaboration, right? If you want to design a robot that's going to collaborate with a human, the best way to do that is to design the controller and have the robot's motion be intuitive to that of a human. So if you look at this visual perception of stiffness and you understand that this mechanical impedance is something that people can perceive, now you can go ahead and write robot controllers that are consistent with how humans perceive their own motion. So why does this matter? I think the biggest takeaway from this talk is that when working with humans, it's important to understand how you can exploit and misuse mechanical impedance. Taking the previous example of human-robot physical interaction that motivated the direct force control experiment, we showed that when you control a robot in a way that's incongruent with the human internal model, the human will have a hard time interacting. However, if you understand that mechanical impedance is an aspect of the human motor action controller and take this into account when designing your controller, you can exploit mechanical impedance. So in conclusion, I have shown that mechanical impedance is a part of the motor action, motor perception coupling, and I've specifically shown that mechanical impedance is necessary to model human motor action during physical interaction. I've shown that subject's ability to estimate stiffness using visual observation of motion demonstrates that stiffness is a part of humans' internal perception model, and that humans' ability to perceive this stiffness is robust to non-vertical velocity profiles. And lastly, I've shown that mechanical impedance can serve as both a bug and a feature. But however, it's important that you understand this and you utilize it correctly. So lastly, I want to thank my collaborators, James Hermes, who's a recent graduate student who just graduated, in fact, from our lab at MIT. Megan Huber, professor at UMass Amherst, who's formerly a postdoc in our lab. Pauline Maurice, who's a research scientist at Loria. Dagmar Sternad, who's a professor at Northeastern, and my advisor, Nova Hogan. I'd like to thank my funding sources. And lastly, I'd like to thank you guys for listening to this talk. If you ever want to reach out to me, you can reach out to me via LinkedIn, which is you can find via this QR code. And then if you're interested in reading either of the papers, the motor paper in the motor action domain, you can find it in via this QR code. And if you're interested in reading the paper on the visual perception of stiffness, you can find it via this QR code. Thank you.
Thanks, Aaron. Wonderful talk. So those who are working in this area, especially me, definitely have questions. So we are open for the Q&A session, and I would request those who have questions to raise their hand, and I can call them up sequentially. Or they can unmute themselves also if they want. So let them first decide the questions. I think they are on it. I have few questions, Aaron. So firstly, thank you for the talk. And in your slide number 14, you have shown a control law. So can you just go there? Yeah, so here you are claiming that you have two attractors. One is with respect to the endpoint coordinates and one is with respect to the joint coordinates, right?
Correct.
So did you use the same to validate the 1/3 power law also, which you had mentioned in the next slide, to simulate the 1/3 power law?
Yes, this control law. So in fact, when you have this control law or superposition of impedances, and you control input, which is an ellipse or a circle, which is composed of two sinusoids or two oscillatory primitives. In fact, the 1/3 power law comes out of that, and I think that can somewhat be seen in this graph here, where we didn't prescribe the specific velocity profile. However, what came out is that we saw there was slower around faster around the straight edges and slower around the curves.
Actually, my I mean, the question was that if you include that one-third power law within that control law, then how do you approach for the convergence proof? Because you have dependent coordinates there, right? Like the x depends on q, uh, the end effector coordinate depends on the joint coordinates, right? Like how did you approach the convergence proof? Did you prove it theoretically also?
Convergence to what?
Like the desired path that you are trying the robot to follow.
So the robot doesn't follow this desired path, in fact. Um, Sorry, I guess I glossed over that point. So yeah, these two attractors do oppose each other. So you can imagine if this wasn't the nominal configuration, but if the joint space attractor is pulling the hand to or pulling the arm to a given nominal configuration, let's say this is the configuration. If you could imagine, now we have the endpoint attractor pulling the arm to some space, I guess here, then those two things are opposing each other. So in fact, I guess what I did not explain well was that the profiles that the arm ended up following looks like so, based on the control law that was described in the previous slide. So for a simulated elbow stiffness of 0 Newton meters per radian, it looked like this light blue line. And then for 50 Newton meters per radian, it looked like this dark red line, like so. So the motion was not circular.
Okay. And
Does that answer the question?
yeah, somewhat. Maybe I will try to relate further later on. So my next question would be, how do you think like this area of visual perception of stiffness is going to evolve in the coming years? Like how you are planning to work on this topic later on?
Yeah, so I think there's a lot of interesting avenues. I think I alluded to one of them being specifically for rehabilitation. Uh, so I don't think I have it. Sorry, I don't think I have the subject. Um, Sorry, give me a second. Yeah, so one interesting point is if I can make this big. When we look at, we had one particular subject who did this task really well. This subject who, okay, I can't highlight it. This subject here, I guess it's probably hard to see on your screen. We see a coefficient determination of 0.9, pretty high. And in fact, this subject was a physical therapist. And I think when you talk about therapy, people often try and quantify this thing they call muscle tone. And there's abnormal tone and normal muscle tone. And I don't have I think in our group, we're kind of trying to figure out a way to prove the hypothesis that when physical therapists are talking about tone, it's somewhat related to muscle impedance or normal and abnormal, maybe muscle synergies, which can be, obtained from normal and abnormal muscle impedance. So that all that's to say is that one of our best subjects to do this task is a physical therapist. And if we can now find a way to do this task, or without a human present, then we can create a system that can say, okay, we can now find abnormal, normal synergies and quantify performance for patients who are going through physical therapy.
Okay, so that answers. We have a question from our audience. Alinja, you can go ahead.
Hello.
Yes,
Yeah,
you're
I
on.
have a question. Thank you for this nice talk. So, as I understand that you have shown these results for arm, like arm in contact with external objects. So, are similar kind of experiments possible, or I mean, are they useful if I consider the legged contact, like the feet contact with the ground, and doing the same? Uh, doing the same, I mean, trying to understand the stiffness in those contacts, for those contacts. So are they useful, or if useful, how can one proceed? If you can share some light on that.
I think let me go to that's not the slide, sorry. So I think the answer to your question is it is useful. However, I think what is important is how you think about the problem. So I haven't studied too much about leg and motion. And I think, so generally in upper limb motion, in upper limb studies, free reaching is a well-studied task. Once you get into contact with things, that things become more complicated. And this is an example of trying to study a task with contact. Walking, for example, in legged locomotion is always coming in and out of contact. So you have those complexities there. So I think I think something similar can be done where if you want to study different aspects of stiffness in walking, maybe you want to have a walking manipulator and try and see can people actually estimate stiffness from this walking manipulator. However, what's important, as I tried to iterate throughout the talk, was that your controller has to be somewhat consistent with how humans actually control their own motion. So I think that's the subtlety where I don't have the knowledge to say, how can you set up this experiment with a walking manipulator, and what aspects of your simulated walking controller are important?
Yeah, and on that note, I just have another question from your slides. That you just mentioned that this your work can be used for rehabilitation. So, can you share some light on how are you planning, if possible, if it is okay for you, can you please share a little bit on that?
How I'm planning to use it for rehabilitation?
Yes, yes.
So I know Professor Huber at UMass Amherst is more so working on this idea for upper limb. I'm looking at some different things for the hand, which I didn't get a chance to present today, so I won't go into details of that. But for the upper limb, essentially, I guess what I was trying to allude to or trying to say in the previous question was that when uh, one aspect of it's not necessarily using for like helping someone rehabilitate, it's more of a tool to quantify progress during rehabilitation. So I'm imagining, let's say we send someone at home, and one aspect of rehabilitation, maybe let's say they suffered a stroke and they're trying to rehabilitate their arm motion in some plane. Oftentimes the rehabilitation task that people will have to do is repetitive motions in different degrees of freedom. Now, when they go to a physical therapist, the physical therapist can be like, "Oh, your muscle dynamics are still off. You're doing this task, quote unquote, incorrectly. Your tone is not normal." What this is trying to do is trying to create a way where now you can go ahead and record this information. You can record this information, and a computer can tell you, you know, this tone is abnormal. And I think the I guess two steps. The first step in that would be, I guess, one thing I'm imagining is that you can just take a camera and you can have someone do their rehabilitation exercises, and camera via, maybe open pose or something can measure the kinematics. It can come out with this estimate of stiffness and be like, and come out with these estimates of stiffness and say this stiffness is normal, this stiffness is abnormal. I think the more subtle beautiful part of that is because we're using computers to quantify, we now don't live in the binary domain of normal versus abnormal. We have a spectrum of how abnormal, how normal.
Thank you. Thank you so much.
Thank you, Alinger. Do we have further questions from our audience? So we do have Professor S.K. Saha with us. He's from Department of Mechanical Engineering, IIT Delhi. Sir, can you hear us?
Yeah, I can hear you, but I'm in the train traveling.
Yeah, he's
Go ahead.
traveling, but he has found out time to join with us. He was there at the end. So, sir, Aaron is from MIT, who has just given a talk on mechanical impedance. And Aaron, just to inform you, we have at IIT Delhi a new technology innovation hub, which is being set up on uh, robotics, collaborative robotics. And Professor Saha is heading that project, and it would be uh, a great thing if we can have collaborations in the aspects of rehabilitation robotics or other cobotics areas with our hub. So that would be a very interesting aspect. Professor Saha, you would like to throw some light or some words?
Yeah, thanks, Sudan, and thanks, Aaron. Actually, this hub we are already working with NSF US. There are 12 projects going on where NSF provides fund to the US PIs and we fund to the Indian PIs. And rehabilitation is, of course, is one of our brand projects where 10 professors from India are working. I think some of them are also part of this joint activity with NSF. I think it will be nice to see something. Maybe there is another call will be coming up very soon, and there might be a workshop in US in the month of May. So if that happens, I would like to communicate with you people, and you might join there. Or if you're planning to come to India, would love to host you. And in this connection, I would like to share if some of the technologies you want to test it out in India, I would be happy to help you. If there is some startup who want to have a business in India, would like to not only help, but we can fund also. No? So these are in brief. More if there are further interest, we can have separate dialogue in some other time. Thank you.
Thank you, Professor
Thank
Saha.
you.
So finally, from the Control Conclave group, I would like to call upon Professor Iyengar, who is our head of the department here, to give some final remarks to Aaron. Sir.
Hello. Thank you, Michael, for this wonderful talk. At least you introduced nicely the mechanical impedance concepts as well as these visual cues for estimating the stiffness. Okay, it's good that generally in electrical engineering domain we are familiar with image processing, visual cues for some other topics, but here is an interesting link between visual cues and the stiffness estimate. I'm sure all participants are being benefited with your talk, and that's very nice. Thank you very much. And I think if you are in Delhi, please contact us. So we can have a joint meeting as well as you can host also for some time. And so thank you, Michael, for your talk. Over to the.
Yeah,
Thank you
thank
for
you,
your
sir.
time.
Yeah, and this is a small certificate from our Control Conclave group for giving your time here. And with this, we'd like to end the talk. And I wish this is just an initiation of collaborations between IIT Delhi and MIT, and we'll have further talks and collaborative works going forward. So thank you everyone for joining in, and hope to see you in the next talk. Thank
Thank
you.
you.